Okay, let's get started. Hello, this is Kyungbin Ryu of INTapt, the master's degree, and today's host. Today we're going to host a seminar presenting the content of the defense presented by Yun-Sub Yun. And let's get started. Let's give her a big applause first.
Hello, I'm Yun-Sub Yun, and I have a presentation about deep learning-based approach for enhanced non-linear speech recognition. So these are contents for today's presentation. I will introduce briefly what ASR is, what the problem of current ASR system is, then I will present this rules motivation, idea, and detailed method. Then experimental setting, the edges, and evaluation will come next. So before we use end-to-end deep learning-based method of ASR, we combine several modules for ASR system. First, extract the feature from audio which helps to perform ASR, and based on these features, perform acoustic modeling. And input is distribution rejected from acoustic modeling, and the reject from language model, which is performed independently from the acoustic modeling part, we are both into the decoder, and we can get the text transcription on the input audio from the text decoder. So this is how traditional ASR is performed. However, recently, the pre-trained and fine-tuned paradigm, which is started from the field of NLP, shows significant performance. So the framework is like this. Based on the large-scale unlabeled data, perform pre-training first, and then fine-tuning with small-scale labeled data. And there comes out many words which also apply this process to speech field. In other words, using a large amount of audio without any label, we can get some speech representation. And then using the small data with audio and associated transcript, we can fine-tune and then the pre-trained model to get the ASR.
Can I stop just for a second? Can you stop for just a second?
Yep.
Can you go back to the slide? So this slide needs to be modified just a little bit more, I think. Because what you're trying to say is you have a model which takes unlabeled data, and I guess that's audio, and produces a speech representation, which is maybe a vector or some tensor. Okay?
Yeah.
And then you try to describe fine-tuning this model. Okay? Now, here again, it's taking labeled acoustic data. Okay?
Yes.
So it's the same as the above figure, but it's producing. Okay, so now where is the model in here? That needs to be updated. So the model is not this green thing. It's somewhere embedded in this thing. And this big, the figure at the bottom is producing words or phonemes. So this green thing cannot be a model because the input-output relationship on the top is acoustic audio that is producing some vector. The bottom is taking similar audio and producing words, which is different from the top. So the model that you're talking about in the top, in the above figure, cannot be this green thing in the figure below, because the input-output relationship is different. Now the model that you're talking about above needs to be somehow represented in the figure below.
Oh, maybe then I need to add some layer on top of the model, the previous model, because the model architecture and the weight group is the same, and there will be addition of the one layer to get the
Right.
Yeah,
So
I
you need to
revise this.
Yeah, you need show that, okay?
Yeah,
Or-
yeah.
And also, rather than saying model, I don't think, is model a good, okay, you can use, I would just suggest, yeah, okay, so if it's a model, then the figure at the bottom needs to have a model and then something else that produces the word, okay?
Yeah, okay.
Do you understand what I'm trying to say?
Yeah, yeah, sure.
Yeah. And because the label, okay, and the label or the transcript is the words, right? So
Yes.
you're trying to use the transcript.
Yeah, yeah.
So this line needs to be updated.
Yeah, yeah.
Because,
I
you
will
know,
update it.
if you want to, what do you call it, present this work again, it needs to be presented in a correct manner.
Yes. So the previous published speech models like WebTuber 2.0 or Hubert are trained with this pre-trained and fine-tuned paradigm, and this model shows unprecedented performance on native English speech, which gives only 2 to 4 points of error rate. However, when native and non-native speakers speak identical text, this model shows some limitation like this, which gives higher error rate on native speakers. So, and this reduces the effectiveness of current high-performance ASR system for real-world application. To deal with
Can I
this,
stop you just for a second there?
yeah,
Can I just stop you? In the previous, here you took a very specific, okay, first of all, I just like to say, from your previous slide, you don't talk about ASR. You talk about model and then fine tuning. And then all of a sudden, this slide has ASR. Okay?
Yeah.
So in the previous slide, maybe you should combine this and say, this is the ASR. Okay?
yeah,
So you need to have a model in here. You need to show what ASR is in here. Okay? And then the next slide, go to the next slide. Can I see the next slide? Then we can talk about ASR, right?
yeah,
And then here, what you're trying to say is that you're looking at a particular kind of ASR, which is, I guess, ASR based on pre-trained model, Hubert.
yes.
Okay? So, what is Hubert representing in the previous slide? Hubert is which is Hubert in the previous slide? If you had to, relate.
Maybe this
What would be
model will be the Hubert, represent the Hubert, but I didn't.
The Hubert is that?
Yes, but I didn't explicitly explain this. I think I need to update this.
Okay, so please make the slide so that model, and a model of, maybe you should have so this is ASR and a model Hubert has been blah 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 and explain a little bit. Okay?
Yeah.
And then go to the next slide. Then you show this, can you show the figure? Yeah. This is based on Hubert, right?
Yes.
This result. 들립니까?
네, 들립니다.
이 결과는, so this result, this graph is based on Hubert, right?
네, 맞습니다.
So I think you need to be specific. What you need to state is, I'm looking at particular kind of a model. you say, Hubert, is why you're focused on Hubert. What is the significance of Hubert? 내가 얘기하는 거 혹시 끊기나 아니면
아니요, 잘 들립니다.
어?
네, 잘 듣고 있습니다.
잘 들리니?
네네.
그래서 이해하겠어? 그러니까 지금
네네.
이 결과는 휴버트를 이용한 ASR이지 다른 ASR은 아니야, 그렇지?
네, 맞습니다.
So you need to be precise.
네.
So you need to explain Hubert, the significance of Hubert, and also that this result is based on Hubert.
네.
Okay?
네, 알겠습니다.
네. 그 다음에
계속할까요?
네.
네. To deal with this problem, there have been various previous works. For example, there are works about fine-tuning one model on diverse accents, or having a separate model for each accent to get a accent-specific model, or using a regularization losses to achieve robustness to accent. However, there are some limitations, which is these methods require updating the pre-trained model weights, so these have expensive computation costs or stretch several models, and catastrophic forgetting on native speech also happens.
Can I just stop right here? First of all, in your previous slide, you defined the model as something that takes the acoustic and produces a representation, right? That's how you define the model. Now here what you're trying to say is it takes these acoustics and the model produces English transcription. So that's a little kind of funny. So what you're trying to say is this model plus something gives you speech, right?
Yes.
And so you want to be a little bit more precise in saying that. And this, the first figure and the third figure, the third figure has TC plus lambda regularizer. Why do you want to do a regularizer on the third one? What is the motivation of using the regularizer?
Also, to get not just fine-tuning on the CTC laws, there are a paper that using regularization. So they propose some regularization laws to get some robustness to the accents.
Robustness to the I don't. Okay, well, okay, now, then in the bottom, it doesn't relate. Why would you get catastrophic forgetting?
Because we need to fine-tune all the model weights, then it loses the information about the pre-trained mode, the information about the previously fine-tuned the information that which is about the native English
Okay, but so
speakers.
then you're mixing a lot of things. So here, this does not correspond to any of the things that we're talking about above.
Maybe I need to explain more about the tuning process, because these are all contain the information, but I didn't explicitly explain about that, I think.
Okay, so
Yeah.
you need to put that, okay?
Yeah,
You need
I
to
will
put
do.
that the training in there, and then you can talk about catastrophic forgetting, okay?
Yeah.
So, okay, and yeah, I think that if you have a training figure in here, then I think it would be better explained, okay?
Yeah. So this study obtained the motivation from the prompting to improve speech recognition performance for non-native speakers without degradation of ASR performance for native speakers, which previously showed good performance. So what is the prompt? Prompt is a new paradigm that originated in the field of NLP. So it is the method of inducing the model to output as we want by providing an approach prompt along with an input without updating the pre-trained model. So there are two ways, which are prompt engineering and prompt tuning. So to find the appropriate prompt, so in the case of prompt engineering, it requires designing a prompt in the form of natural language that people can understand and their form through explanation of the task or concrete examples. And the prompt tuning and the prompt engineering is to go through a trial and error process to find a better prompt. In contrast, prompt tuning puts embedding type prompts into the model along with the input and learns the prompts using algorithm-based method. So compared to the prompt engineering, the interpretability is relatively small because the prompt tuning uses an embedding rather than a natural language form, but it has advantage of obtaining an optimal prompt without trial and error using a trial and error process because it is using a data. The method proposed in this study, information theory adversarial prompt tuning for enhanced non-native speech recognition, which is called INTapt. The general idea is shown in figure on the left, which visualizes a hypothetical accent feature space. So in general, in figure as in A, the accent features.
Just a second. In the previous slide, you also used this model of, in your second slide, remember you used model as acoustic, then the representation.
Yes.
Here again, it's after the tune model, it needs to go to some classifier to produce the speech.
So you could just repeat it again, I couldn't understand.
Okay. But it's not really important here. Okay.
Can I go next?
Yeah, please go. Oh, sorry.
Yeah.
Yes.
So the idea of this study is to bring the accent feature of non-native speakers closer to the accent feature of non-native speakers through the prompt as in B. So in other words, by concatenating the prompt with the input data and inputting it into the model that has already been trained with the native speaker speech, this method makes the model consider that the non-native speaker speech has similar accent to that of the native speaker speech. So it enables improvement of speech recognition performance for non-native speakers' utterance. That is, L2 speech without degrading the performance of native speaker speech, that is L1 speech. So next.
Can I just stop you just one more the previous slide?
This one?
Yeah. So you have these clusters in A where they're spread apart, right?
Yes.
But after this processing, the clusters are more, they're gathered a little closer.
Yes, they are closer to the native
right?
accents. Yes.
그렇게 돼 있잖아, 그치?
네, 맞습니다.
근데 위아래가 이게 그 색깔이 뭘 얘기하는 거야? 그러니까 위에는 녹색, 노란색, 파란색으로 돼 있고 아래는 그 녹색,
네네.
이 노란색이 녹색으로 바뀌었다는 얘기인가?
네, 약간 노란색이 녹색에 가깝게 바뀐다 이런 얘기를 표현하고 싶었습니다. 이게 프롬프트를 붙였기 때문에 이것과 동일하진 않고 이게 어디로 가까워지냐면 녹색과 가까워진다 이렇게 표현하고 싶어서 색깔을 바꿨습니다.
근데 잠깐만 여기에 이렇게 좀 얘기하면 약간 헷갈리는 게 뭐냐면 사람한테 어떤 인상을 주냐면 it's showing that the green just stays where it is and only the yellow and the blue are coming a little bit closer. But what you want to say is that everything moves. Everything moves.
But
The
in
green, the yellow, and the blue move. All of them move, and they are closer together.
But in here, the green one means the native
도
speech.
아니잖아. 그 자리를 그냥 그대로 유지하는 건 아니잖아.
근데 여기에서 이 초록색은 네이티브 스피치이기 때문에 자리를 거의 그대로 유지합니다. 프롬프트를 붙이지 않고 네이티브 스피치는 자리를 그대로 유지하는 것이 맞습니다.
네이티브 스피커도 유지를 프롬프트를 붙일 거 아니야.
ASR을 수행할 때 프롬프트를 굳이 붙이지 않아도
근데 만약에
네.
이 시스템이 모든 스피치에 대해서 이것도 먼저 한번 봐야 돼 내가 봤을 때 모든 스피치에 대해서 그냥 돌아가려고 하면은 그것도 좀 그런데 네이티브는 프롬프트를 안 붙이고
네이티브에 프롬프트를 붙여서 성능이 거의 유지되는 것은 이미 확인이 되었는데 이 그림에서 표현하고 싶은 거는 이제 악센트 피처가 네이티브는 악센트 피처가 바뀌지 않는다.
그건 알겠어. 그건 알겠는데 나는 이제 어떤 인상이 있냐면 이 그래프를 봤을 때 프롬프트를 이 피처 스페이스가
네네.
피처 스페이스에서 차지하는 이 녹색이 프롬프트를 붙여도 움직이지 않고 그대로 있다는 그러한 인상을 준다 이거지.
네. 네.
이 전체적으로 프롬프트를 붙임으로써 그 공간도 바뀌고 공간도 바뀌면서 세계가 같이 가까워진다는 그러한 그림을 그리는 게 더 낫지 않나 그런 생각을 내가 너한테 한 거야.
네, 알겠습니다.
이게 주는 인상은 이게 가까워지나? 그러니까 이걸 조금 과장되게 조금 표현을 했으면 더 낫지 않을까 하는 생각도 들거든.
네.
이게 그러니까 그 노란색의 그룹들이 조금 가까워진다. 그러니까 위에 있는 거를 예를 들어서 거리를 나타낸다. 여기 표시에 거리라는 걸 D라고 또 표시를 해놓고 아래쪽에도 D 프라임이라고 해놓고 위에 있는 그 D에 비해서 D 프라임이 더 작다는 거를 뭔가 좀 그러한 표현을 조금 얘기를 해주면 좋을 것 같아. 이 그림은 약간 이게 진짜 가까워졌나? 가깝게 하려면 좀 확실하게 좀 가깝게 하고 멀리 있으면 확실하게 멀리 해서 그 내용 전달이 확실히 되면 좀 좋겠다는 거겠지.
네, 알겠습니다.
무슨 말인지 알겠니?
네네.
그렇게 좀 과장된, 그러니까 어차피 사실은 아니잖아 이 그림이.
네네.
과장되게 좀 표현을 했으면은 그 내용 전달이 확실하게 될 것 같다는 생각이 좀 있어.
네, 알겠습니다.
Okay, let's go.
So I will explain detailed method.
진입장해 주세요. 일단 하고 있습니다.
So So I'll explain the details of the method. So INTapt incorporate two-step training process. First step is training accent module that can extract the accent feature from audio feature. And the next step is training prompt generator that generates input-dependent prompts, and this prompt will be inputted into the model with original data. So these are annotations used in this method. So F refers accent module, PG refers prompt generator, and these are variables. And here H is hidden states that are extracted from the middle layer of the backbone model. For this hidden state, we wanted to use low feature of data, in other words, the acoustic feature in audio. So we used lower layer hidden states of backbone model. And the backbone model is transformer architecture that is already trained on native speech for the purpose of ASR. So let's go into the detail. First, the accent module is trained to extract accent feature. We use the hidden states that I mentioned in previous slides, and by incorporating two objectives, we get this model. The first objective is accent classification. So we will classify speaker's errand. So for example, when my speech is inputted into this part, this model needs to classify my speech as Korean. And the second objective is accent intensity regression. We consider that the intensity of an accent could vary among different people and between utterance from the same speaker. So the accent intensity information needs to be considered to get the accent feature. And for the accent intensity, we employ the CTC loss, which is utilized to train backbone model for ASR system as a proxy accent intensity. This is based on the hypothesis that larger accent intensity, higher CTC loss, and when the accent of certain utterance is similar to that of native speakers, the CTC loss would be low.
Recording in progress.
Sorry. Go ahead.
So we train accent intensity regression hat to predict the CTC loss of the input utterance. And by incorporating these two objectives, we train accent module and we could retain accent feature for prompt generator. Next, prompt generator module that generates input-dependent prompt embedding. It uses same hidden states input that used in the accent module. As the prompt, the output of prompt generator will be concatenated into the audio feature together and perform ASR test. This prompt generator was trained with two objectives. First one is mutual information minimization and CTC loss minimization. The first objective, mutual information minimization, is to reduce the mutual information between the accent feature obtained when the prompt is concatenated and the accent feature obtained from the original utterance. This prevents the backbone model from recognizing the accent that the prompt contains in the original utterance. At the same time, the prompt generator is trained to reduce the second objective, which is CTC loss minimization. That is, CTC loss widely used to learn ASR. And the backbone model trained with native speaker speeches to generate the prompt that can improve ASR performance. And this makes the backbone model recognizes that the accent of non-native utterance concatenated with a prompt is similar to that of the native speaker. Therefore, by combining two objectives, mutual information and CTC loss minimization, to learn a prompt generator, when a prompt is input along with a non-native speaker's utterance, the model recognizes the non-native speaker's utterance as if it is close to the native speaker's accent. And this can be improved the ASR performance. And the overall explanation of after the overall explanation of the method, I will tell you about the explanation settings. The non-native speaker dataset used in this study is L2RT dataset, which has in total 24 speakers, including 2 female, 2 male speakers from 6 countries. And the 6 countries are China, India, Vietnam, Korea, and Spain. This is a dataset in which the speaker reads the same text. And additionally, in this study, the R-charted dataset was pre-processed assuming the natural data collection situation. So when collecting the data, considering that it is common that the amount of the data collected for each accent could be different. So we split them into 3 groups. First one is more frequent accent, which is using all training data, and the next one is least frequent accent, which are using half of the training data, and last one is unseen accent. And the evaluation metric is the word error rate, which is widely used in the speech recognition test. Compared to the reference, the number of words changed, deleted, or added in the mover prediction was calculated and represented as the error rate. In addition, the backbone model used are Hubert and Hubert large, X large, and both models are pre-trained using unlabeled data and fine-tuned using a rebel speech, which is composed of native speaker speech. And the setting we compare performance are the following 3. First one is fine-tuning. Is a general fine-tuning situation when the backbone is fine-tuned using L2RT dataset. And prompt CTC is the prompt generator is learned using only the CTC loss minimization. And the INTapt is when the technique proposed in our study. The first experimental result is experimental from the L2RT dataset. Despite the relatively small number of the parameters compared to the fine-tuning, prompt CTC and INTapt, which are prompt tuning methods, shows a good performance compared to the fine-tuning. In addition, INTapt shows better performance than prompt CTC, which was trained using only the CTC loss. And we can see that the prompt tuning technique has greater effect when the backbone model is larger. And the second experimental result is performance on liberal speech benchmark consisting of native speakers utterance. It was tested on both situations divided into clean and other depending on the level of the noise in the recording situation. And all performance means that the result from the both clean and other setting. In the case of the backbone model, since it was trained through the liberal speech training data, the error rate shows good performance in range of 2 to 4.2%. In contrast, when fine-tuning was performed on the native speaker data, the error rate increased significantly. Both prompt tuning methods shows increase in an error rate of less than 1%, and it can be seen that prompt tuning effectively improves speech recognition performance for non-native speaker utterance and does not cause performance degradation for native speaker utterance. And the following is an example of improved speech recognition. So this is ground truth transcript, and the next case is the backbone does not make a proper prediction, and next one is when the prediction is corrected by INTapt. So for example, GT is shouted, and backbone predicts as a shoulder, and INTapt predicts shouted as it correctly. And the next one is ovulation study. So first ovulation study is visualization through test and plot whether the accent feature from accent module actually containing only the accent information. So we extracted the accent feature for speakers from India, Korea, and Spain, and each country includes 4 speakers. So looking at the plot, it is difficult to distinguish cluster based on the gender, but as each country for the country, they are well performed the cluster. So it can be seen that the accent feature actually contains only accent information without additional information about the speaker. And using this accent module, whose effect was confirmed in the previous ovulation study, we actually checked whether the utterance of a non-native speaker and the accent feature of the native speaker are similar through the INTapt. So blue represents the similarity of the accent feature between L1 and L2 speech when no prompt is attached. The purple one is the similarity when the prompt CTC method is used, and the yellow one is similarity with the L2 accent feature obtained by the prompt generator of our method. So as you can see, the yellow shows the highest similarity in all cases. That confirms that INTapt can effectively make the mover recognizes accents in non-native speakers utterance similar to the native speaker utterance. So
Can I ask something? Can I just 여기에
네.
노란 거는 새로운 거를 제안했을 때 뭐와 같은 거야?
그 네이티브 스피커로부터 얻은 악센트 피처랑 인트앱을 결합했을 때 이제 얻은 악센트 피처의 시밀러리티가 높아지는 상황입니다.
아, 그러니까 이 구조를 이용해서
네.
네이티브 스피커랑 그 액센트 피처랑 어느 정도 같냐를 나타내는 거야.
네네, 코사인 시밀러리티를 맞습니다.
그러니까 그러면은 그 얘기가 좀 그러니까 지금 between L1 and L2X L1 and L2 accent는 뭐지?
L1이 네이티브 스피커의 악센트고요. L2가 이제 L2 스피치, non 네이티브 스피커의 악센트입니다.
그러면 그 얘기를 쓰는 게 좀 좋을 것 같아. L1, L2 하니까 약간 좀 헷갈렸어.
아, 네.
어?
네, 알겠습니다.
그리고 이거는 average score를 시킨다.
네, 맞습니다.
아니 여기 highest similarity 여기가 그 있구나. just one accent. 이게 조금 더 그 위에 있는 그 슬라이드 딱 잘 보이게끔 좀 돼 있으면 좋겠어.
아, 요 밑부분 여기 말씀하시는 거예요?
근데 거기 있는 거 말고 여기는 위에다가 딱 볼 수 있도록 좀 해주면 좋겠어.
아, 네, 알겠습니다.
TSN이 그것도 하지 않았어?
네, TSL 플랫 앞에서 했습니다.
오케이.
So finally, to summarize, this study proposed a prompt tuning technique based on information theory to prevent performance degradation of native speaker speech while improving speech recognition performance of non-native speakers. Through the proposed technique method, it was proved that prompt tuning can help improve the speech recognition performance of non-native speakers and shows better performance than Python. In addition, it's also shown that by using an information theory-based objective, the model can recognize the speech of a non-native speaker as having a similar accent to that of the native speaker. Thank you for listening.
We assessed any questions. For those in offline, you can raise your hands, and those in online, you can turn off your mic. Any questions? Waiting for a question.
온라인에는 나 혼자인데 그 다른 사람들 다 와 있나?
웬만한 사람들은 와 있습니다.
Is there
Okay,
any?
I think it was this very good work, very good work. As I said, if you can, have a YouTube or something, that would also improve the citation. So after this is going to be published, so what you should do is try to make the citation as high as possible. And I think people will look at this paper if it's I don't know publicized a little bit better. Okay, so you should have it maybe on YouTube. You should also have code that's available. That would improve citation.
네, 알겠습니다.
And also, you should try to upgrade your final manuscript in any way possible.
네, 알겠습니다.
Okay, wonderful job, wonderful job.
Can we accept further questions? If not, thanks for the nice presentation, and I again congratulate you of the successful defense. Let's give a big applause and wrap up.